I'm the calculus professor, and today I'll be talking to you about arc length. Alright, in problem number 28, we want to find the arc length of the curve y equals ln of x minus the square root of x squared minus 1 for x's between 1 and 2 by integrating with respect to y. Okay, as this thing is set up, it looks like we should integrate with respect to x, but I think we'll find very quickly that that's not very nice. We know the arc length formula, we know we have to square the derivative. The derivative of this thing, first of all, isn't very nice, much less squaring it. It's going to be horrible, and we're not going to be able to take an antiderivative. So the strategy here is, could we somehow write this thing as x equals a function of y? At first it doesn't seem very nice, but it is possible. So what we're going to do is we're going to start out by, let's just figure out what is the curve that I want to integrate. So write x as a function of y. So let me rewrite this over here. This is y equals ln of x minus the square root of x squared minus 1. Alright, and what I'm going to do is I want to solve this thing for x. So first let's raise both sides, make it e to this side is equal to e to this side. And so I get e to the y is equal to e to the ln of something. Well, e and ln are inverses, so I just get x minus the square root of x squared minus 1. Alright, I see that I have a square root here. I'd like to get rid of it, so if I can get it by itself, possibly I can square it. So I'm going to move this x to the other side and write e to the y minus x is equal to negative square root of x squared minus 1. Okay, multiplying both sides by minus 1 gives me that negative e to the y plus x is equal to the square root of x squared minus 1. Let's square both sides. And so I get, I'm going to rewrite this a little bit. I'm just going to write it as x minus e to the y, just because I think it looks better that way. I'm going to square it, and I'm going to square this side, but when I square this side, I just get x squared minus 1. Okay, let's square this guy. When I do, I get x squared minus 2x e to the y plus e to the 2y, because I take negative e to the x times negative e to the, negative e to the y times negative e to the y is e to the 2y. And that's equal to x squared minus 1. Notice that both sides has an x squared, so I could subtract x squared from both sides. When I do, the x squareds go away, and I'm left with negative 2x e to the y plus e to the 2y is equal to negative 1. This is quite nice, actually, because I'm just left with this one x sitting here. Everything else is y. So I could solve for x. So let's do it. If I solve this thing for x, I get negative 2x e to the y is equal to negative 1 minus e to the 2y. Now I can divide both sides by negative 2 e to the y, and I get that x is equal to negative 1 minus e to the 2y divided by negative 2 e to the y. That's not the cleanest thing I've ever seen. I can get rid of the negatives everywhere, and I could break it up into two fractions. Both of those are things that I want to do. So I want to write this as x is equal to, if I just look at negative 1 over negative 2 e to the y, I could write that as 1 over 2 e to the y. And if I look at negative e to the 2y over negative 2 e to the y, then that's just positive e to the y over 2. And that is my function written as x equals some function of y. Now we have some function to work with. Now that we have that function, now we can do all of our calculus using our formula for finding arc length. So really quick, I'm going to erase all this, and we can now use this function to do what we're trying to do. All right, now that we have this function written as x equals some function of y, we are ready to actually plug it into our arc length formula and get an equation. But before we do, we really need to take its derivative. So we need the derivative of this guy, and the derivative here is x is equal to, x prime is equal to, the derivative of e to the y over 2, which is e to the y over 2. And then the derivative of this guy, this is actually an e to the negative y if it were on top. So using my rules for taking the derivative of e to the negative y, I would have negative 1 over 2 e to the y. Okay, so this is my derivative function, and now I'm ready to start plugging in to my arc length formula. So arc length formula, I get integral from some value to some value, and it's tempting at this point to write in 1 to the square root of 2. That would not be a good choice because these are x values, and what I want to have inside here are actually y values. So I need to figure out for these x values what y values would come out of the function. So let's plug in 1 here. If I plug in 1, I get 1 minus 1, which is 0 here, and then ln of 1 is 0. So I get a 0. All right, if I plug in the square root of 2, square root of 2 squared is 2 minus 1. This would just be 1. And then I get square root of 2 minus 1. So I'd get the ln of square root of 2 minus 1. Okay, something interesting here is square root of 2 minus 1 is a number less than 1. And numbers that are less than 1's ln are negative numbers. So this is a negative value. So if we're integrating over here, we want the lower one to be on the bottom. And this is the lower one. 0 is actually bigger than ln of square root of 2 minus 1. So 0 goes on top. ln of the square root of 2 minus 1 goes on bottom. And now we're ready to put in our arc length formula, which is the square root of 1 plus the derivative, which we have right here, e to the y over 2 minus 1 over 2 e to the y squared dy. Okay, let's work on this a little bit. So we get integral from ln of square root 2 minus 1 to 0 of the square root of 1 plus e to the 2y over 4. Okay, 2 times this first guy is e to the y times this second guy is minus a half. Square the second guy and I get plus 1 over 4 e to the 2y dy. This can be rewritten. This is integral ln of square root 2 minus 1 to 0 of the square root of e to the 2y over 4 plus 1/2 plus 1 over 4 e to the 2y dy. And it just so happens that what is under the radical is a perfect square. So let's rewrite it as a perfect square. This is integral from ln of square root of 2 minus 1 to 0 of the square root of e to the y over 2 plus 1 over 2 e to the y. Quantity squared dy. All right, so now that we have this perfect square, we can rewrite this integral. I've got the integral from ln of square root 2 minus 1 to 0 of e to the y over 2 plus 1 over 2 e to the y dy. And that is something that I can take an antiderivative of. Let's do it. This is the antiderivative of e to the y over 2 is just e to the y over 2. And the antiderivative of 1 over 2 e to the y is negative 1 over 2 e to the y. And that's evaluated from ln of square root of 2 minus 1 to 0. All right, the only thing left to do here is to plug things in. I think I'll erase over here real quick so that I can plug things in. So plugging in the 0, we get e to the 0 over 2. Well, e to the 0 is 1, so I get 1 over 2. Plug in the 0, and I get minus 1 over 2. Minus 1 over 2, okay. Minus, now I plug in the ln of root 2 minus 1. So I plug in an ln. If I plug in an ln as a power of e, the e and the ln cancel, and I just get the square root of 2 minus 1 divided by 2. And then I get minus 1 over 2 times now square root of 2 minus 1. All right, so this is my answer, but I'm sure that I can simplify it down a little bit better than this. So I get a 1/2 minus a 1/2, those just cancel. And now I have this, which actually does have a common denominator if I multiply the top and bottom here by the square root of 2 minus 1. So let's do that. Notice there's a negative here. I could distribute that negative if I wanted to. So if I distribute the negative, I get minus square root of 2 minus 1 over 2 plus 1 over 2 times square root of 2 minus 1. I'm going to multiply top and bottom here by square root of 2 minus 1. If I do, I get minus square root of 2 minus 1 squared over 2 times square root 2 minus 1 plus 1 over 2 square root 2 minus 1. Combine those two and I get what? Well, on the bottom, I definitely get 2 times the square root of 2 minus 1. And on the top, what do I get? Well, these are all negative. So I get this guy squared, which is 2, so minus 2. I get 2 times the first times the second, which is positive 2 square root 2. And the second one squared is 1 times a negative is minus 1. And then I add 1. So the negative 1 and the 1 cancel. And I'm left with 2 root 2 minus 2. And on bottom I have 2 root 2 minus 2. That's otherwise known as 1. And so the answer to the arc length on this curve between the two starting points, which I believe were x equals 1 and x equals the square root of 2, is 1. And we're done.